This lecture is on thermodynamics. This is a lecture on thermodynamics. Here we're going to discuss thermodynamics in context of continuum mechanics. To start with, first we need to define a temperature field associated in continuum body. In continuum mechanics, the body we associate a field, a continuous field, a scalar field, theta. We call it, which is a function of position and time. It is a temperature field. It is defined this x that belongs to B of t, a configuration space, we call it Bt, and time t, which is greater than equal to 0. What is temperature? In continuum mechanics, it's a collection of bodies. If we focus on a small area, we can see here there are a lot of particles. These particles have different velocities. We cannot calculate and track individual particles. What we can do is ascribe a mean velocity about this point, which represents these different velocities around this point. So temperature, it is a measure of mean velocity around a point. Mean velocity of particles around a point. So temperature is a method, a quantity that tells us about the mean velocity of particles, of this collection of particles around this specific point. This is a continuous function. Now, it also tells us about the variation of the atomistic velocity near a point. So what is heat that we associate with the temperature field? Heat, we denote it by Q, or we also call it heat content. Heat content is basically a mean energy associated with the velocity fluctuations of individual atoms near a point. So to summarize it, we have two quantities. One is temperature and another is a heat content associated with this temperature field. So temperature field, what temperature field tells us in a continuous body is about this point, we have different velocities. So temperature is a measure of the fluctuation of this velocity around this point, whereas heat, it is the energy associated with this fluctuation. It is the mean energy. It's the mean energy associated with this fluctuation of velocities. Associated with fluctuations of these velocities. So we have two quantities, temperature, which tells us about the mean fluctuations of the velocity near a point, and we associated another quantity with this temperature field, heat content, which gives us the mean energy associated with this temperature. So now move on to discuss the next topic that we have. Let's consider an arbitrary open subset. Omega t at configuration space Bt We denote the quantity net heating by the symbol Q, and here we denote the open subset that we are considering. Net heating is rate per unit time at which heat is being added to this subset that we are dealing with at present. Rate per unit time at which heat is being added to this configuration space, not configuration space, but the subset that is in the configuration space BT. We can decompose Q into two parts. This net heating, Q of omega T, can be decomposed into two parts. One is the body heating, and another one is the surface heating. We assume this body heating to be a linear function, to be a continuous function, assume this body heating to be a continuous function of the volume. And this quantity here, that is Q sub S, we call it surface heating. In the layman's term, we can understand it by this way. Suppose this is our body, a three-dimensional body. Heat can be applied from the surface. It can come into the subset from the surface that we call Qs of omega T, and it can generate it from within. We call this body heating. So our net heating is decomposed into two parts. That one part that is influx to the surface, and the other one that is being generated from the body within the body. Now we're going to assume another field. Now we are dealing with the body heating. At present, we are dealing with the body heating. We can describe body heating like this integral, by this integral, R of x comma t. R is a field, which I'm going to come and describe what this is. We are integrating over this subset, omega t is a volume integral, dvx. This R of x of t, it is the heat supply field per unit volume. We call it heat supply field per unit volume. So it is the heat source, the field, that is creating the body, that is responsible for body heating. This R is body heating, but that is for the 1 unit of area. So if we want to find out the body heating for entire dvx amount of volume, what you have to do, we have to integrate it over this subset omega t. So this part is our body heating part. This R of x of t, which you call the heat supply field per unit mass, notice there are two different R. The R with a hat over, this is the heat supply per unit volume. But we want to deal with heat supply per unit mass. Heat supply per unit mass. So the relationship between R hat and R hat is heat supply per unit volume. There's something by volume. And R of x of t, which is the heat supply per unit mass. We have, if we want to go from this per mass to per volume, what we have to do is to multiply with the density field xt, because it has a unit of mass per volume. So we can cancel these masses. What we yield is per volume, which is our left side. So The integral can also be represented. We know that r hat is rho, the density field, times the body heating per unit mass. So our body heating over the subset omega t is a continuous integration of rho, the density field, x comma t, r of xt, which is the body heating per unit volume, per unit mass, the dvx. So this is the integral representation of our body heating part. Now what we have in our plate is the surface heating part. Surface heating we denote it by Qs omega of T. We're going to represent it in a similar fashion by a continuous integration, but as it is a surface integration, so as we can expect, it will be a surface integral. So we're going to associate another field, which is called the heat transfer field per unit area, heat transfer field per unit area, which is h of x comma t, which belongs to the real space R. So my Qs of omega t, this is the surface heating part, it will be on the boundary of partial of omega t. This is not partial omega t, this is a symbol, delta of omega t, which denotes the boundary of this volume enclosed. This volume is denoted by omega t, and the surface is denoted by del omega t. This is a surface integration of this heat transfer per unit area quantity, which belongs to the real space, which is a function in R, dAx. But as surface area comes into the picture, we want to create something that has a vector-like nature. So this is a scalar field hxt, which further can be described by a vector field q x dot t. Now we dot with the unit vector n. The unit vector n is the unit vector of the surface. This is a surface, and this has this unit vector n. And this quantity, this vector quantity, it is named, it is called the Fourier-Stokes heat flux vector. Fourier-Stokes heat flux vector in configuration space Bt. We have a configuration space, and this is our Bt. And this is omega t, that the system of subset that we are dealing with. What we are doing is we are considering a volume. This volume has the surface, this volume is bounded by the surface del omega t, which has a unit normal, outer unit normal n hat. And suppose the heat is coming into this direction, we describe it by vector q. So this n and q is in the opposite direction, hence we put a minus sign. We put a let me get the eraser. We get this minus sign in front of this expression, which indicates that if Q is inverse, then Q is negative, then H, the heating, is positive. If Q is outward, then Q dot N is positive, but there's a negative sign in front of them, so H will be negative. So if heat is coming in, then it is positive, the H is positive. If heat is going out, then H is negative. Following this convention, the integral expression that we have for our body heating and surface heating, the net heating can be described by this expression. U of omega T is our body heating and our surface heating. Our body heating has the integral representation omega T rho of x comma T R, which is the heat supply field per unit mass that we have encountered previously, x comma T. It is a volume integral because it is a body heating which deals with the entire body. The body is heated because of a field that is within the body. And the surface heating. For surface heating, we have the expression Q is a vector x comma T dotted with n, the outward unit normal, over the surface area. It is integrated over the surface, del omega T. So this is the final expression we have for our total net heating. Let's box this expression. Let's use a box expression. So this is the expression for net heating. The next thing we have on the plate is the kinetic energy power of external forces and net working. The topic that we're going to deal is kinetic energy, power of external forces, and net working. Net working. Again, let's consider, suppose we are in this space. We call this configuration space BT. Let's take a subset. Here we're dealing with the subset omega T with the surface del omega T. This arbitrary open subset we are considering. This omega T is the arbitrary open subset. This open subset and this comes from real analysis. If a set satisfies certain properties, we call it open subset. Open subset of BT, the configuration space BT. As we are dealing with kinetic energy, we have to take consideration about the forces. So force, we have two kinds of forces. One is the body force that acts as a force per unit mass, and another force that comes from outside that acts on the surface. The force per unit area that acts on the surface, we call that traction. T of x comma T, we call this external traction field. This is the force per unit surface. External traction field. This is the force on a body per unit surface. And suppose we have another field. This is the body force field, a vector B of x of T. This is the external body force field per unit mass. External body force field per unit mass. What you're going to do, I'm going to motivate the expression for the power. First, define the kinetic energy of this open subset, omega T. Our good old kinetic energy expression is half times mass times velocity, but that is for a particle. That is also true for a continuum body, but you have to modify it a bit. Here, the mass per unit volume is rho. So per unit volume, the kinetic energy is the density field rho of x of T into the velocity field v of x of t squared. But we have to take in consideration that this is not a point particle, but rather we're dealing with continuous body. So I have to integrate it over the entire volume. So this is the expression that we have for kinetic energy. Now power, we know that power is force times velocity. This is the power we know from our good old Newtonian days for a point particles. But we have continuous particle now. We have continuous mass now. So the expression also gets modified, and we seek to represent it by integral expression. So power of this open subset will be the force times velocity. But we have force per unit mass. So how about the power per unit mass? The power per unit mass would be the force per unit mass times the velocity. This gives us the power per unit mass. What is the mass? But we don't have any expression for mass per unit volume, so we have to multiply it by density field. This is our mass. So this expression gives the power per unit volume, but we have continuous body, so we have to integrate it over entire volume, dvx. This force is the body force. So this power is due to the effect of body force. But we have another force, that is the traction force. So you have to give the same treatment, similar treatment for traction. This integration is over the subset omega t. But the traction, we have the traction field T, this is a vector, x of t, this is the force, traction force per unit area. We have to multiply it by V to get the power, and also as it is a continuous body, so we have to integrate it over the entire area over the bounded surface. This is our final expression for power. This is our continuous integral representation of power for a continuum body. Let's put a box around it. So what you can see is that power, it is a result of two agents. One is the body force, and another one is the traction field. So what is on networking? The concept of networking is a word that you do. Networking is denoted by omega t. The word that you do, some part of it gets absorbed by the continuous body that doesn't set it in motion, and another part sets in motion. So what networking is the total power that you deliver minus that part that is responsible to set it in motion. That is, we have to deduct the kinetic energy part from the networking. So networking has a unit of power. It has a name of working, but it has the unit of power, because this has the unit of power, and this is energy by time that also has unit of power, that is joule per second. It is joule per second, and it's also joule per second. Now we are all set to dive into our first law, and internal energy. So the next topic we're going to cover is the topic of internal energy and power. What is internal energy or energy content? The internal energy or the energy content is that part which is not associated with kinetic energy. It is the energy of the body excluded the kinetic part. Again, consider a subset, open subset. Omega t in BT, and of this subset, we associate a potential energy U of omega t. We're going to assume this omega t is a continuous function of volume. So these are the extensive properties. The extensive properties are those properties that depends on the size of the system. So this potential energy is also dependent on the information of the size of the system. We're going to associate a field that is phi x comma t. We can put a hat that is a real function. This is the energy density field per unit volume. This is the energy density field per unit volume. So our total internal energy is this energy density integrated over the entire volume, omega t. So this expression is for energy density per unit volume. So what is the energy density per unit mass? What you have to do is to multiply it with density. Then you get energy density per unit mass, per unit volume, sorry, which you denote by a hat. So this U of omega t, the continuous integration of phi x of t, we're going to replace phi of hat by this expression. So here we have previously phi hat, which is going to be replaced by phi and rho x comma t, which is integrated over dvx omega t. So this is the expression that we have for internal energy, the integral expression that we have of our internal energy for a continuum body, under the assumption that this U possesses the extensive property, that it depends on the size of the system. Now we're going to give our axiom. So this is axiom 1. Based on this preliminary discussion that we have exposed to, we have axiom 1, that is the first law of thermodynamics. What the first law of thermodynamics states is that the total net heating that you do, plus the net working, omega t, it causes to change the internal energy. So this is the expression or the statement of first law. This is the heating, and this is net heating, and this is the net working. The net heating and net working that you do, it causes a change in the internal energy. But now we know that the net working, W, can be written as W equals to P minus dk dt. We're going to use this fact and substitute for W. That is Q of omega t plus P of omega t equals to d dt of omega U of omega t. This dk dt, which should be here, we have taken this expression to the right side, that is d dt of k of omega t, which also can be written as d dt of U of omega t plus k of omega t equals to q of omega t plus the net power delivered omega t. This is the net heating part, and this is the power delivered part. This is the expression that we have for our first law. The net heating and the net power delivered causes a change in internal energy, and it also causes change in kinetic energy. We associate a potential with the power delivered, the external work that you do by delivering this power. We want to describe it by a scalar function. If we take the derivative of this function, it gives us the net power delivered. This G is called the potential energy for external force. Here we are just going to deal with mechanical forces and thermal forces. There can be other kinds of forces like electrochemical forces, electromagnetic forces. For the time being, we are not taking that into account. Another thing is that the kinetic energy concept of continuum body is based around the fluctuating velocities around these points. So this is not the velocity, this is not the energy associated with the individual atomistic velocities, but rather this is the velocity, this is the energy associated with the mean fluctuation of velocities. This gives result to this mean energy. Whereas in the case of a particle, we take the energy associated with the velocity of that particle. So there is a huge striking difference between the kinetic energy of particle and kinetic energy of a continuum body. So we're going to put this expression of P back into this equation here. For P, we're going to substitute the value of P by ddt of G, a potential associated with the external forces. What we end up is ddt of U of omega t, K of omega t, and G of omega t. That is equal to Q of omega t, which states that the rate of energy, rate of change of total energy, this is the total energy, this is the total energy, E total, of omega t. So the rate of change of total energy is equal to the net heating. This term is the net heating term. So if the net heating is zero, then we can say that the rate of change of total energy is zero. One shortcoming of this first law is that it doesn't put any bound of the rate at which this energy can change. To answer this question, the second law comes into the picture. If we have time, then we're going to explore this topic in the near future. Thank you for today.